This is a higher tier momentum and stopping distance set of questions. It says triple here, but it's actually good for triple and trilogy. So ignore this, but let's crack on. So question 1, an investigation was carried out to show how thinking distance and braking distance and stopping distance are affected by the speed of a car. This is a classic question, so follow this through. There's 19 marks here, so it should take about 19 minutes, but I'll try and do it a bit quicker than that. The results are shown in the table. So we've got speed in meters per second, we've got thinking distance, we've got braking distance, we've got stopping distance. And it says, draw a ring around the correct answer to complete each sentence. As speed increases, what happens to thinking distance? So as speed increases from 10 to 30, for example, what happens to the thinking distance? 6, 9, 12, 15, 18. Well, it increases. So there's the first answer. As speed increases, braking distance does what? Well, as speed increases, what's happening to the braking distance? 6, 14, 24, 38, 55. Well, that's also increasing. So those two are nice and easy. One of the values of stopping distance is incorrect. Draw a ring around the incorrect value in the table and then calculate the correct value. Well, if you look at it and you remember, stopping distance is going to be thinking distance plus braking distance. So 6 plus 6 is 12. 12 plus 24 is 36, etc. These are all perfectly fine. The one that's wrong is this, because this should be 23, not 43. So 9 plus 14 is 23, not 43. So the correction is we put a ring around that, 43, like they've asked us to. It says draw a ring around it and then correct it. So we've corrected it here, 23. Using the results from the table, plot a graph of braking distance against speed. Draw a line of best fit through your points. So here we're told that that's the braking distance in meters. We're told that this is the speed in meters per second. So all it is a case of plotting your data. So when the speed was 10, the braking distance is 6. So I plotted that there. And then we've got 14, 24, 38, and 55. And then we draw on a line of best fit. Remember, the best thing to do is put your hand in the middle of the arc and then draw your line as a nice smooth arc around there. Okay, it might mean you turn your paper around to get that nice smooth curve. Again, it doesn't matter if we miss a point. We're not trying to join the dots ever. We're trying to draw on the best line of fit, the line of best fit for those points. Okay. So that would get you 3 marks, just drawing it like that. And what we're looking for as examiners is where your points are, and we can usually give it to within half a square. So you've got to be pretty accurate. You've got to have a nice sharp pencil. And then we're looking for 1 mark for the line of best fit, and that will give you the 3 marks. And then it says, use your graph to determine the braking distance at a speed of 22. So I've gone to 22. I've looked at this and I said, right, there's 20, there's 25, and there's 10 little squares between them. So each little square must be a half. So that's going to be 20 and a half, that's 21, that's 21 and a half, that's 22. And I've indicated on my graph where 22 is. I've then gone up from 22, and I found it crosses at that point. I've then gone across from that point, and I found it's 29. Because on here, you've got 10 divisions between 20 and 30, so that's nice and easy. Each one of these is 1, so I get up to 29. So that's my braking distance. Then part D, the speed time graph for a car is shown below. So speed time is speed there, time along the bottom. Time is usually an independent variable, so it usually goes along the bottom of a graph, remember. While travelling at 35 meters per second, the driver sees an obstacle in the road at time t. So at this point here, at time t, they see the obstacle. So I could draw a little eyeball there to show me what's happening at time t. The driver reacts and brakes to a stop. Determining the braking distance. Okay, so there's quite a lot to think about here. So we've got 2 regions. We've got a flat region, and we've got this, ignore this purple one for now, we've got this black line here. So there's nothing happening between 0 and that point in terms of the speed. The speed doesn't change. So that indicates the period of time where the driver has seen the object and is reacting. So that there is the reaction time. They haven't pressed the brake yet. So this is the period of time that's the reaction time. So I then go down to there and work out what that number is there, and you get 0.6. Again, there's 0 to 1 is 10 little divisions. So if there's 6 little divisions, that's going to be 0.6 seconds. So I've got a time of 0.6 seconds there, and that's when we put the brake on. And remember, we're trying to find the braking distance. And the braking distance is the distance travelled from applying the brake, in other words, at that point there, to the point where it stops. In other words, the speed is 0. Now you then look at the graph and say, well, where does it stop? It stops after 4.6 seconds. So it starts at 0.6 and it stops at 4.6. So the time difference between those is going to be 4 seconds, which is what I've indicated here. 4.6 minus 0.6 is 4 seconds. So my braking time is 4 seconds. So I've got this equation, distance equals velocity times time. We're trying to find the distance, so we're trying to find S. We've then worked out time from the graph, it's that 4 seconds. And we've got the V from the question, it's 35. So, I'm going to use the area under the graph. I've written it here. So I'm going to use the distance travelled being the area under this graph here. So it's that there. Okay, so I've got 4 seconds along the bottom, and then I'm going to do half of that, and then I'm going to times the height, which is 35. So I've got half of 4 times times 35 equals 70 metres. All right. Now, we can't just put these numbers in as 35 multiplied by the time, because that velocity is changing all the time, which is why we need to use the area under the graph. Okay. Okay, on to part 2. If the driver was driving at 35 metres per second on an icy road, the speed time graph would be different. Add another line to the speed time graph above to show the effect of travelling at 35 metres per second on an icy road and reacting to an obstacle in the road at time equals t. Well, if you look at the graph, if it's icy, that's not going to affect the reaction time. You're still going to see it and react in the same period of time. We're going the same speed as well, so we travel the same distance. So this is going to be exactly the same. But we're going to take a lot longer to stop. When we put the brakes on, because it's slippy, it's going to take longer to stop. So anywhere down here above 4.6 and your graph is going to be fine. So if it's a straight line going from that point at 0.6 seconds, which is the reaction time that stays the same, as long as your graph ends up beyond, so less steep in other words, beyond the 4.6, and this would be a correct answer. Okay, so that's part 2. I've written down same reaction time and speed. So thinking distance is the same. We've got reduced friction though, which means the braking distance increases, and then I've shown that on the graph. Part E, a car of mass 1,200 kilograms. Remember, physicists, we're always looking for the data. 1,200 kilograms, that's the mass. Travelling at 35 metres per second, calculate the momentum. So we look up momentum on the formula sheet. If it's a year, we're given the sheet, which this is, and the next few years will be. At one point, they might say you've got to learn them again, but if you have to learn them, you've just learnt that. Momentum P equals mass times velocity. You look for the mass, which is 1,200. You multiply it by the speed, which is 35, and you get 42,000. And then the units are the units for mass, which are kilograms, and then the units multiplied by the units meters per second. Now, in some books, I've never done this before and shown this, but it sometimes appears, you sometimes get books putting a little dot between the kilograms and the meters per second. So we don't usually put anything in there. We don't put the times in. We certainly don't put a dash saying divide by, because that's wrong. But kilograms meters per second is what we're looking for there. So that is the correct unit for this. It's really easy, isn't it? 1,200 times 35 is 42,000. You get 3 marks for that, even on higher tier. And then the car stops in 4 seconds. So we've got another bit of data. We know that the momentum has changed by 42,000 kilograms meters per second. And we now know the time it took to change. So the time is 4 seconds. We've got this equation as well. Ft equals delta P. So the F times T, which is sometimes called impulse, always called impulse, is equal to the change in momentum delta P. All right, which is the final momentum, we could call that mv, minus the initial momentum mu. But we often write it as just a delta P. It's nice and neat. And our change in momentum, which we can look back at what we did up there, we found it to be 42,000. So our change in momentum is 42,000, which means our F times T is 42,000. So therefore our F, which is what we're trying to find, always keep bearing in mind what the question is asking you for. It's asking you for force. So we can rearrange this equation and put it in that form. F equals delta P divided by T. Delta P, which is the change in momentum, is 42,000. The time is 4 seconds. So 42,000 divided by 4 is that, okay? 10,500 newtons. And that will get you 2 marks. And that, all of that, is 19 marks. So that's pretty massive. I would make another video with the next question, which is coming up, about the air-driven toy, but that is it for now.